So now let's talk about evaluating limits of rational functions at infinity. So remember that a rational function is a polynomial divided by a polynomial. So to evaluate the limit as x tends to either positive or negative infinity of a polynomial p of x over another polynomial q of x, divide the numerator and denominator by x to the k, where k is the degree of the denominator. Okay, what's that saying? Alright, well, let's take a look at an example. The limit as x tends to infinity of the quantity 6x squared plus 2x minus 5 divided by the quantity 2x squared minus x. We look at the degree of the polynomial in the denominator, and it's 2. What we want to do then is divide the numerator by x squared and the denominator by x squared. So whatever the power on x is, that's what we're going to divide by. Whatever the highest power of x is here, we're going to divide everything by that power of x. So we'd have the limit as x tends to infinity of 6x squared divided by x squared plus 2x over x squared minus 5 over x squared over 2x squared divided by x squared minus x divided by x squared. Let's clean this up a little bit. So that's going to simplify to 6 plus 2 over x minus 5 over x squared, and that's divided by 2 minus 1 over x. So, now let's take a look at this. This expression should be algebraically equivalent to what we had before, except that, well, actually it is equivalent. I was going to say that this one cannot be, you cannot substitute 0 in here, but you can't substitute 0 in here either. But it doesn't really matter because we're not really interested in x equals 0. We're interested in large values of x. Okay, so what's going to happen to the 2 over x and the 1 over x and the 5 over x squared as x gets really big? Well, they're going to get really small. How small? They're going to tend to 0. And the answer is 6/2, or 3. Now let's think about where this 6/2 came from. It came from this 6 and that 2. And where did this 6 and that 2 come from? They came from that 6 and that 2. They came from what we call the leading coefficients of those two polynomials. The coefficients of the highest power terms. And actually that's what tells the whole story in a limit like this. You can tell just by looking at those terms what the power is going to be, what the limit is going to be. Well, let's take a look at another one. You've got the limit as x tends to negative infinity of 2x minus 3 over 2x squared plus 7x minus 9. Is the answer going to be 2 over 2, which is 1? Be careful. Let's divide everything by x squared. That's the highest power of x down here. And I'm going to try to leave out a step and see if you can fill in the details. If I divide the numerator by x squared, I should get 2 over x minus 3 over x squared. And then the denominator will be 2 plus 7 over x minus 9 over x squared. As x gets really big, that goes to 0, that goes to 0, that goes to 0, that goes to 0, and the answer is 0 over 2, which is 0. It's not 1. The degree of the numerator and the degree of the denominator are not the same in this particular example. The degree of the denominator is bigger. And so what's going to happen is the denominator is going to grow faster than the numerator, and the limit will be 0. So if the degree of the numerator is less than the degree of the denominator, the limit will be 0. If you're dealing with polynomials. Let's take a look at another one. You've got the limit as x tends to infinity of 8x cubed minus 5. That's all divided by 4 minus 9x. Divide everything by the highest power of x in the denominator. That would be x. And so this is going to be the limit as x tends to infinity of 8x squared minus 5 over x divided by 4 over x minus 9. That goes to 0, that goes to 0. Now, what we've really got is this. We've got the limit as x tends to infinity of minus 8/9 x squared. The 8x squared divided by minus 9 is the same thing as minus 8/9 x squared. Now what's going to happen to that as x gets big without bound? Well, x squared is also going to get big without bound. Then you multiply that by a negative value. If you want to say that this limit is negative infinity, I can live with that. If you want to say that this limit does not exist, I can live with that. And let's try one more of these. The limit as x tends to infinity of 3x squared minus 2x sine x divided by 6x minus 7x squared. We're going to divide everything by 7x squared, or rather just x squared. So if we divide everything by x squared, we're going to get 3 minus 2 sine x over x divided by 6 over x minus 7. I hope you see where that comes from. Now, we know that that's going to tend to 0, but do you remember the limit as x tends to infinity of sine x over x? We said that that was 0. And so what we've got is negative 3/7. So now we're going to look at some limits involving square roots, and there are a couple of things we need to discuss before we delve too deeply into these limits. And so the first one is, if x is greater than 0, then the absolute value of x squared is equal to x. So for instance, if you have the square root of positive 4 squared, that's going to be the root 16, which is 4. You might remember that this notation, this radical, means we want the principal square root, which is the positive one, if there is one. And if x is negative, then radical x squared is equal to negative 1 times x squared. So for instance, if we had, say, negative 4 squared, well, that's still going to be radical 16, which is 4, which is not the same thing as this negative 4 we had here. In fact, it's actually negative 1 times negative 4. So if you're dealing with a negative value of x, this thing is going to be positive. Radical x squared is going to be a positive value, and x itself is going to be negative, so minus 1 times x is going to be positive. So you need to keep the signs in mind. Another thing to keep in mind is that the square root of a over b is equal to the square root of a divided by the square root of b, or radical of a over b is equal to radical a over radical b. This also works if the operation is multiplication instead of division. So if you have radical AB, that's the same thing as radical A times radical B. And this assumes that A and B are positive numbers. Alright, so let's take a look at figuring out what this limit is. We've got the limit as x tends to infinity of the square root of the quantity 100x squared minus 5x plus 2, and then we're going to divide that by the quantity 7 minus 2x. So you want to do the same thing we did before. Divide by the highest power of x in the denominator. Well, the highest power of x in the denominator is x to the first. So I'm going to divide the numerator by x, and I'm going to divide the denominator by x. Alright. So if we divide the denominator by x, we're going to get 7 over x minus 2. Now what about the numerator? Well, we can't just divide what's under the radical by x and be done with it. It doesn't work that way. We can use this idea. We can divide one square root by another square root and then combine them into a single square root, and then we can divide what's under the radical. But what we've got to do is rewrite this x we're dividing by as a square root. Now, we're looking at the limit as x tends to positive infinity. So are we more interested in the positive values of x or the negative values of x? The positive values of x. So if x is positive, that means that the square root of x squared is equal to x. And so this x is equal to the square root of x squared. Now, since we've got a square root divided by a square root, we can turn that into a single square root. And so we're going to end up with the square root of 100 minus 5 over x plus 2 over x squared. And then that's going to be divided by 7x minus 2. Alright, now everything with an x in the denominator is going to tend to 0 as x gets really large. So we're going to have the square root of 100 divided by negative 2, and I think that will be negative 5.